In this video, we're going to look at how to sketch cubics in all their forms. There are two main forms to watch out for. We have the inflection point form, and we have all of the factorized forms. This will be a bit of a longer video, so feel free to skip through the chapters if you're looking for something specific. For those who don't know me, my name is Chris Iannazoni. I used to work as an engineer for a defense company, and I've since left that to start a career in tutoring. I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. First type of cubic we're going to look at is the inflection point form cubic. Just like how a quadratic has a turning point, a cubic has an inflection point, where the inflection point is just that little bit of a wobble that the cubic has in the center. The good news is that, other than that, all the other terms in the inflection point form work identically to that of the quadratic's turning point form. Let's have a look. The dilation factor A is responsible for stretching the graph vertically. If A is greater than 1, then we observe the graph to become thinner. If A is between 0 and 1, we observe the graph to become wider. When it comes to hand drawing these graphs, you're pretty much going to ignore this term every time. You're still going to draw the exact same shape every single time that you hand draw it. It's still worth knowing what the term does to the graph, because when it comes to your investigation secs, you will need to be able to explain what it does. Reflections are identified by a negative sign either out the front of the entire function, or directly attached to the x variable. The interesting thing about cubics is that a reflection in the x-axis looks identical to a reflection in the y-axis. It's for this reason that you'll only ever see a negative sign at the front of the cubic, because both reflections are mathematically identical anyway. Just like quadratics, the h and k terms are translations. If you have x minus h, that represents a translation to the right by h. For example, if you had x minus 1, that means you're shifting the graph to the right by 1. If you have x plus h, you're shifting the graph to the left. For example, if you have x plus 2, you're shifting to the left by 2. Vertical translations are determined by the k term. If you have plus k, then your graph is going upwards. For example, if you had x cubed plus 1, then your graph is being shifted up by 1. If you have minus k, then your graph is shifting down. For example, if you have x cubed minus 2, then your graph is being shifted down by 2. You can also have both types of translations in the same function. For example, this function has x plus 2, meaning it's a shift left. And it also has a plus 1 at the end, meaning we're shifting up by 1. In all circumstances, when it comes to sketching inflection point form cubics, we need to know three features. We need to know the axes intercepts, the endpoints, and the inflection point. The advantage of the inflection point form is that we can use it to find the inflection point immediately. By observation, we can see that x plus 1 means a shift left by 1, and the minus 3 out the front means we're shifting down by 3, giving us a new coordinate of -1, -3. Now we move on to the axes intercepts. The y-intercept is always found by subbing in x equals 0, and when we do that, we're going to get a result y equals -1. X-intercepts are always found by subbing in y equals 0 and then rearranging for x. The only thing I want to touch on here is that whenever you take the cubed root of a number, there is no plus minus. That only applies to square roots. Let's take a quick detour to explain why. The square root of 4 just means I need to find two identical numbers that multiply together to give 4. There are two possibilities for that. You can have 2 and 2, or you can have -2 and -2. That's where the plus minus comes from. When it comes to taking the cubed root of something, for example, the cubed root of 8, there's only one possibility there, 2 times 2 times 2. If you were to try -2, you would get -2 times -2 gives you +4, and then +4 times -2 gives you -8, which is not the same thing as 8. Therefore, there's only one possibility for the cubed root of 8, and that is 2. That also brings up the second point that I want to mention, which is the fact that the cubed root of a negative number does actually exist. We just saw what the answer was. The cubed root of -8 is -2. Anyway, back to the solution. We actually can't simplify that x-intercept anymore, so all we're going to do is sketch the graph to go through all the key features that we mentioned. Once you have all the key features, there's really only one way that you can draw the graph and have it still look proper, but if you're ever confused on what the shape is, there is one rule of thumb. If you have a positive cubic, it has to start at the bottom left and end at the top right. If you have a negative cubic, it has to start at the top left and end at the bottom right. Ours is positive, so it's going to start bottom left, end at top right. This will be important later when it comes to sketching the factorized cubics. As a final note, let's have a look at what happens if you restrict the domain. When you restrict the domain, you now have to find the endpoints of your function. rather than shoot off to positive and negative infinity. In this example, we're restricting the graph between -2 and +1/2. Finding the endpoint is just a matter of subbing in each of those x coordinates and then getting the corresponding y coordinate. Once you have that, you're just going to cut the graph off early and then draw the appropriate circles at each endpoint. X equals -2 is going to get a full circle because it was included. It had square brackets. And x equals 1/2 is going to get an open circle since the brackets were rounded. They were excluded. Not all cubics actually have inflection points. Some of them have 2 turning points instead. These kinds of cubics are those that can be factorized. There are 3 main things to consider when it comes to sketching these types of cubics. The first is going to be the sign of the overall cubic. That'll tell us the shape of that cubic. And then we look at if it has linear factors or if it has repeated linear factors. In all cases, we're using that information to solve for the axes intercepts and the overall shape. We're going to look at some examples of all of these things. If your cubic has linear terms, then those linear terms are x-axis intercepts, and you solve those through null factor law. In this case, we have 3 linear terms, so we have 3 unique solutions. When it comes to the y-intercept, you're solving that like you always have, by subbing in x equals 0. And in this case, that gives you y equals 6. Now it comes to figuring out the overall shape of the cubic, and we do that by looking at the signs of each of the individual x terms. In this case, we have 3 positive x's. Thus, we have a positive cubic. And positive cubics, as I mentioned earlier, start at the bottom left and end at the top right. The graph that you draw is then going to look something like this. You start at the bottom left, and then you're going to go through your first x-intercept at x equals -2. Then it's going to come back down through the y-intercept. And then finally, it's going to finish up by cutting through the remaining 2 x-intercepts before finally finishing at the top right. If we had a negative cubic, like this one here, which has 1 negative x and 2 positive x's, then it's going to start at the top left instead and end at the bottom right. One final thing I'll mention is that the negative x doesn't necessarily have to be attached directly to the x. It can actually be factorized out the front, like this one here. Although this still has 3 positive x's, the fact that there's a negative sign at the front makes it a negative cubic again. One thing I want to touch on before we leave this example is the overall shape of the turning points. Until you learn calculus, you're not going to be able to figure out where those turning points are. In the last example, we will look at how to find those points with calculus, but only watch that example if you already know how to use calculus. Some cubics have repeated linear factors, which just means that you have a linear factor that is squared. These factors are also x-intercepts, but more specifically, they're also turning points. Let's see what that means. As before, we're going to find our x-intercepts by null factor law. This time we're only going to get 2 unique solutions. The y-intercept is once again solved by subbing in x equals 0, and this time we get y equals 8. Finding the overall shape of this cubic is a little bit different. There's actually 3 positive x's here, even though it might not look like it. There's 1 from the linear term, and there's 2 from the repeated linear term. The net result of 3 positive x's means we have a positive cubic, meaning we start at the bottom left and end at the top right. Like I mentioned earlier, notice how we now turn at x equals 2, rather than going right through it. This is due to the fact of it being a repeated linear term. Now we look at the worst case scenario, or perhaps, depending on how you look at it, the best case scenario, where one of our terms is a quadratic that can't be solved. All this means is that when it comes to solving your x-intercepts, that quadratic contributes no solutions. By the way, if you're ever confused on whether or not a quadratic has solutions, then you can always check its discriminant. If you get a negative result, then you know for certain that that quadratic has no real solutions. As for solving the y-intercept, that never changes, you're just going to sub in x equals 0. Same thing for the shape of the graph. We see we have 1 negative x and 2 positive x's, hence the result is going to be a negative cubic, meaning we start at the top left, end at the bottom right. The problem is that we have no idea what the rest of the graph looks like. Without the CAS at hand, or without an understanding of calculus, we have no idea how to draw the rest of the graph, so you're literally just going to draw a squiggle, wherever feels right. It is a bit of a hacky workaround, but this really shouldn't be in a test that's pre-calculus. The only reason I mention it is because I have heard stories of this stuff happening before. Just make sure that you have these criteria. You're going to start at top left, end at bottom right, go through x equals 1, go through y equals 1. As long as you have all of those key features, your graph is going to be fine. Alright, this is the final example. This time we're going to use calculus. So, as before, we're going to use null factor law for the x-intercepts and x equals 0 for the y-intercepts. We can see it's a positive cubic, so we're going to start at the bottom left and end at the top right. Now for the calculus bit. Finding the turning points of this cubic is a matter of finding the derivative and then setting the derivative equal to 0, since all stationary points have a gradient of 0. The easiest way to find the derivative of this function is to first expand it all the way out and then use the power function derivative. Now that we have the derivative, we're just going to set it equal to 0 and then solve. I'm going to use the cross product method to factorize it and then use null factor law, but feel free to either complete the square or use the quadratic formula, either works. These x solutions that we just found are the x coordinates of the turning points. So to find the corresponding y coordinate of the turning point, we're going to sub in those results of x into the original function, not the derivative function. Now that we know where they are, it's just a matter of sketching the function with all the information we collected. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.